Okay, welcome back. Let's quickly explain where we were. So we have a notion of infinity spaces, which are special functors from finite pointed sets into spaces satisfying the Siegel conditions. Uh, and we have spectra. And we have a functor, omega infinity, from spectra to E infinity spaces. Oh, sorry. For some reason, okay, I decided to spell space explicitly, so I probably should keep doing it. In this sense, E to the functor omega infinity, sigma infinity blank tensor E. And this is a monoid. It is in space because spectra has direct sums and omega infinity respects products. So omega infinity of E plus F is omega infinity of E times omega infinity of F. Because it's a right adjoint. So you can see that indeed it has the property, one of this functor omega infinity E has the property, another way of phrasing the Siegel condition is that it sends wedges of finite pointed sets to products of spaces. Okay, so this should be easy, and it's also obvious to see that it preserves limits, so we expect it to have a left adjoint, which it does, which is this B infinity. Which sends M to the spectrum Bn, where I used the previous lemma to show well, I'm not sure I needed the previous lemma for this. Oh, no, I didn't. Sorry. But this is... But where I used a lemma to say that if M is a commutative monoid, an infinity space, then Bm also has a canonical infinity space structure. So while before, when you had an E1 space and you take the classifying space, you just get a pointed space, what's sometimes called an E0 space. For an E infinity space, if you take B, you get an E infinity space again. Okay. Okay, and now I promised you that I would show you that B infinity and omega infinity indeed are adjoint, and to prove the recognition theorem using this fact, which is really, really easy once you have this adjunction and what we already did. So, okay, questions about this?
Yeah, could you quickly remind me how we defined B? Just did I remember?
Remember Bm, so remember if M is a monoid, Bm was just the colimit over delta M, delta op, sorry, of M. But okay, now if M is a commutative monoid, I actually, okay, I didn't say it like this the other way, but maybe it's easier to say that this lands in monoids, in commutative monoids. No, okay, this probably is confusing. Let me say Bn, I want Bm of I plus. And I'm going to say this, the colimit over delta op of M of I plus wedge this gap blank plus. And remember this gap blank plus was just a functor from delta, from delta up to finite pointed sets that we used to get an E1 space out of an infinity space, a set of gaps. And every gap is sent to the set of gaps every gap is sent to the gap into which it falls, if there is one, or to the base point otherwise. I think I spelled it out explicitly last time. It's in the notes anyway. Okay, so that's the definition.
Excuse me, by E infinity, you now mean commutative monoid?
Yes,
Oh, okay.
I think I always use this terminology. I might have made some mistakes at some point. A commutative monoid in spaces is what's called an infinity space. It's a historical terminology, but it's also snappier to say than to say commutative monoid in spaces. So,
okay,
I'm using it. And also, if I say, oh, I just take a commutative monoid, people might think I'm talking about commutative monoid in sets, and it's even worse when you say an infinity group. People might think it's a group in sets. So I think I'll stick with using the traditional terminology for clarity. Okay, but is this clear? And use the fact that colimits over delta up commutes with products. To show that this is indeed it satisfies again the Siegel conditions. Okay, questions? So the first thing I'm going to do is to give you a map M from omega infinity B infinity M. And that's actually quite easy. So I think I should call this eta. Because this, if you look at the definition, this is just omega of B of M. And I already gave you such a map. But now using the fact that I can use the easier structure on omega is going to be even simpler to give it as a map of commutative monoids. Because I just need a diagram. Of commutative monoids or E infinity spaces. And that's fairly easy. I just write it down what the functor is. So here I'm going to take the constant functor at 0 plus, which is again a commutative monoid, and it clearly receives, I mean, it's a terminal object, so it clearly receives a map from M of I plus. This includes this, sorry. Which is just Bm of I plus. I just need to give you such a diagram for every I in a natural way, and that's, well, there is only one possible such diagram essentially, so. That's what you obtain. I mean, you can see these as I plus mesh 1 plus if you want. And you the same way in which I defined it in the case I is the point, you can get the same definition for every I, and it's naturally in I. Okay. Good. Okay, so this gives me eta. And the other map is slightly trickier to define. In order to do that, first I'll construct an epsilon map that doesn't go from B infinity omega infinity M, but from B omega M into M. And if you remember, I already defined such a map when M was a space. And in fact, I just take for every I plus, I take the map of pointed spaces we already constructed. And this is natural in I because it was a natural transformation of pointed spaces. So now claim this epsilon and eta and epsilon satisfy the triangular identities. And they do so because they did that pointwise. And you can check that everything was natural. And so B is left adjoint to omega. Now, omega from commutative monoids to commutative monoids is just the loop space. Functor in commutative monoids in spaces. So these forces, B is the suspension from commutative monoids space into commutative monoid in spaces is the suspension functor. So the pointwise, the loop space is computed as in spaces, but the suspension is not computed as in spaces, this other classifying space functor. So this B infinity notation that I chose was analog to the notation for sigma infinity, and it's not a coincidence. It's because it's essentially the same kind of construction. Only it's easier because commutative monoids are closer to spectra than spaces were. Okay, now I want to get a map B infinity omega infinity E into E. And how do I do that? Well, I need to give you for every n a map Bn omega infinity E into the nth space of the spectrum, which I'm going to write like this. Remember, this is just the nth space. And I need to give them in a compatible way. It's just that the obvious diagram, I mean, I also have to provide you with homotopies of the obvious diagrams, but they will come for functoriality. So I need a map of pointed spaces, and I'll do something more. I'll give you maps of commutative monoids. And we choose, the underlying maps on spaces, maps on pointed spaces, coming from the map of E infinity spaces adjoint to the equivalence omega infinity E goes to omega n, omega infinity sigma n E. So this is, if you want, E0 equivalence to omega n En, which we have because E was a spectrum. So that's kind of tricky if you want, but really not much is happening. So I need to give you a map of pointed spaces. Well, I'm going to give you a map of commutative monoids. In particular, this is going to give me a map of pointed spaces. And this map of commutative monoids, using the fact that B was the suspension in commutative monoids, is just adjoint to an obvious map. Okay. So let me call this also epsilon. Maybe it's this, even the same name is a bit confusing, but it's a map in a different category. So the first was a map of commutative monoids, and this is a map of spectrum. So hopefully there is not going to be ambiguity. Questions about this construction? No? Okay, then lemma.
Sorry, I'm a little confused. So what precisely are we doing? We do not have the co-unit map yet, or do we have the...
I just defined it. I mean, I haven't proven it's the co-unit map. I haven't proven it's an adjunction yet.
Okay, wait. So, and how did you define this map?
I gave you each component. Okay, to be honest, I also should give you I should also give you the homotopies, but they follow by adjunction. Actually, let me. I actually also should give you a homotopy of the diagram. Sorry, omega bm omega infinity e omega sigma m e. Should also give you a homotopy making the diagram commute, but if instead of trying to construct a commutative diagram of pointer spaces, you try to construct a commutative diagram of commutative monoids, again by adjunction, this is just where was I? Yeah, this is well. It's tautological actually. If you try to show that this diagram commutes a commutative monoids, because it is suspension of omega, suspension of omega where was I? Well, okay. Yeah, sorry. I can use the adjunction and see that this diagram is adjoint in the vertical direction to the diagram with the identities here. And here, this is not the identity actually. And then this is adjoint in the horizontal direction to a diagram with identities everywhere. Well, okay, they're not really identities, they are canonical equivalences in the right vertical map case. But you can play this diagram with the junctions and see that this homotopy has to exist. There is a canonical choice for homotopy. So let me make this small, maybe. But okay. Because what I'm caring about is that lemma, eta, and epsilon satisfy the triangular identities. Again, so there exists an adjunction B infinity, omega infinity. And the proof is, again, not particularly deep. So let's see which one. I want to prove only one of them. Let's see. Yeah, let's check. That this composition is the identity. So this one is omega infinity eta, and this is no, sorry, this is eta omega infinity, and this is omega infinity epsilon. Yeah. Okay, but what this is? Well, this is just omega b of omega infinity e. This is the canonical identification, and this is well, this is omega of the epsilon at the level so I can, so this is omega of epsilon level of infinity spaces. Yeah, if here I write omega infinity as this guy for sigma e, and and this follows from the definitions, because this map is just, yeah. This map in the end is the diagram is commutative with the canonical identifications. So you just get the identity. Okay. But once we have that, you can actually get the recognition principle for connected spectrum. Oh, actually, before I do that, maybe I should define what a connected spectrum is. So I said it already, but let me give the official definition. A spectrum is connective if pi I of E is 0 for all E less than 0. So theorem, which is the recognition principle for connective spectra, and okay, what does it say? It says, so here let M be a commutative monoid in spaces and E a spectrum. So we have a bunch of properties. The first one is this map eta here is an equivalence if and only if M is a group, is an E infinity group. Then B infinity of M is always connective. And the third is that this map epsilon is an equivalence if and only if E is connective. In particular, the adjunction B infinity omega infinity restricts to an equivalence between E infinity groups and connective spectrum. So this, maybe I should say this is subcategory of connective spectra. Okay. Is the statement clear? Okay, now the proof is easy. We give numbers 1, 2, 3. 1, we already did, since we can check it on the underlying monoids. Because remember, this is just the map omega bm. And okay, it is a map of infinity spaces, but to check it's an equivalence, you can check it on the underlying spaces even, but for the underlying monoids at least. And we've seen in the recognition principle for loop spaces, that this map is an equivalence if and only if pi naught of M is a group. So that was actually the hard part, but we already did it. So 2, we just need to check pi of p minus n of b infinity of m is 0 for n greater than 0. But these, remember the definition, is just p0 of bm of n. And again, we have seen that bm of n is connected. And then 3, well, 3 is again very easy. So certainly, since B infinity is connective, if they're an equivalence, E must be connective. So if epsilon equivalence, E must be connective. Vice versa, because B infinity is, if E is connective, epsilon is an equivalence on all non-positive homotopy groups. Sorry, all negative, not non-positive, all negative homotopy groups. And that's because they're 0 for both spectra. So it's enough to check omega infinity of epsilon is an equivalence, but then by the triangular identities, in fact, it's the one I just proven. So here we have omega infinity epsilon, and here we have eta of omega infinity of E. That's an equivalence because omega infinity of E is group-like. And that's the identity. And so omega infinity of epsilon is an equivalence. The end. Okay, and that was the proof. It's very anticlimactic if you want, because we did all the hard work before, but the theorem is an important one. Let me restate a corollary that we saw last time. So we have abelian groups is just group objects and sets that lives inside commutative monoid in spaces, and this embeds into spectra. This is equivalent via B infinity to connective spectra. This, of course, embeds into spectra. And well, what does this do? It sends an abelian group A to some spectrum, some connective spectrum, such that omega infinity of E is A. What does it mean? Well, it means that E can only have pi 0. i.e. pi I of E is 0 if I is different from 0, and A if I is 0. Because, well, we don't have many other, the negative homotopy groups cannot be there because it's connective, and the positive cannot because omega infinity. And so, said differently, this is the functor sending A to HA, to the Eilmer-MacLane spectrum that I described to you earlier. So this is indeed a fully faithful embedding of abelian groups into spectra. Okay. Okay, so let me define two important guys that we get out of this. So if N is a commutative monoid, this I already defined it for monoids, but I have the group completion, which is omega Bn, which is in fact a commutative monoid. Just recording that the group completion stays a commutative monoid. And it's the, and sorry, M goes to M group is the left adjoint to the inclusion. Groups into commutative monoids. Here's the group completion, and that's called the group completion. And it's going to be the protagonist of the rest of today's class. But I want, before I do that, I actually want to introduce another important object, is spectrum. Then I'm going to define its connective cover as B infinity omega infinity E. So it's the connective cover. And this is the, and E goes to the connective cover is the right adjoint to the inclusion of connective spectra into spectra. And in general, I can define the N connective cover, T greater or equal than NE, is just sigma N, T greater or equal than 0, sigma minus NE for every N, in Z. And it is the right adjoint of the inclusion of N connective spectra, that are those spectra that have no homotopy groups in degree N. It is the right adjoint. So these are spectra with homotopy groups all in degree greater or equal than N. So should use pi I E is 0 for all E less than N. This is just because the suspension is an equivalence and it shifts these categories into the next one. So it's not much. And so using this universal property, oh no, sorry, let me say first also the N truncation. I was forgetting about this. Is the cofiber of the map from the N+1 connective cover to E. And this has the dual property that the map from E to the N truncation is an iso on pi star for star less or equal than N, and pi star of the N truncation is 0 for star greater than N. That's because this map has the dual property. This map is an equivalence on homotopy groups in degree from N+1 and everything, and it's the 0 otherwise. Okay, sorry, this was a bit of a barrage as definition. Is it clear what am I doing here?
Maybe why do we need in the definition of N truncation the cofiber, and in the N connective in the definition of N? In the other definition, we simply can forget the other.
Oh, that's because I have this functor here that's coming from our theory. There are other ways of actually constructing this functor by adding cells to kill all homotopy groups, but I like that we can get it from this description. And anyway, it boils down in the end. We have a tower. So E maps to this tower, t lesser or equal than n, t lesser or equal than n minus 1, whose limit is E and whose co-limit is 0. This just follows by playing with the universal properties. And the co-limit is 0 because the homotopy groups do commute with co-limits. And the limit is E. This requires a tiny bit more of care. But since every tower, the sequence of homotopy groups is eventually constant for every degree, the map to the limit ends up being an equivalence on an isomorphism on all homotopy groups, so an isomorphism. In general, there will be a lim1 term, but I don't want to say that. I just want to name this because it's very important. It's the Postnikov tower. And you can think of it as a filtration on E, whose nth layer is the fiber E, which is exactly the nth suspension of H by n of E. Because this map is an isomorphism on all homotopy groups except in degree n, where it's just a map from pi n of E to 0. So the fiber has only one homotopy group in degree n, and it is pi n of E. And so you can filter every spectrum by Allenberg-MacLane spectra. And that's a very important fact. But I'm not sure if we're ever going to use it in this course, probably, maybe later, but it's certainly a very important fact that this is often used, and I wanted to mention it. And this is related to the so-called Atiyah-Hirzebruch spectral sequence. This gives you other filtrations with homology groups that can be, with layers that can be computed in terms of cohomology of stuff. But, unfortunately, time is limited. And I want to give a very short introduction to the properties of group completion, even if I won't be able to do everything. So, questions about this? No. Okay. Good. Okay, so the next topic is going to be group completion. And actually, it's not on the notes yet. I actually wrote a very detailed treatment of group completion in the notes. I'm not sure if I'm going to do all in the class because I want to talk about vector bundles also before Christmas and MK theory. But I have to tell you at least something. So, okay, we defined the group completion, and now the goal is define group completion. Sorry, not define, describe and not define. Completion for nice monoids. So in general, throughout this section, M will be a commutative monoid, an infinity space, and X is going to be a point in pi 0 of M, such that for every Y, there exists a Z with Y plus Z is N times X for some N in Z. Every other point is a summand of some multiple of X. This happens, for example, Well, there are a bunch of examples. The most common is going to be pi 0 of m is the natural number, x is 1. That's a very boring example, but it's like 90% of the examples we will consider. But more generally, if pi 0 of m is finitely generated with generators x1, xr, you can take x just their sum. It's an exercise you can see that is. So this is not crazy. In fact, usually what you do is you write every commutative monoid as a filter colimits of monoids for which pi 0 is finitely generated, and then apply the results that we're going to describe to that setting. But okay, this is the standard assumption. And if you want is an exercise that this x has the property that you want, but it's an easy exercise. And I say finitely generated as a monoid, by the way, not as a group. Means every element is a sum of a bunch of copies of xi's. Okay. In this setup, I can consider this mapping telescope, which is just the colimit of the map adding x. Let me actually define what I mean by this. Well, precisely I mean, well, I have a map m brackets 1 times m brackets 1. Sorry, I have a map x times m brackets 1 into m brackets 1 times m brackets 1, which is equivalent to m brackets, sorry, I'm doing commutative monoids. This whole story has a version for non-commutative monoids, but I'm not going to describe, and this is just a multiplication. So this is just x plus, it's just this composition here. And you might expect, if you know this story from classical sort of commutative monoids, that the mapping telescope is going to be the group completion. Unfortunately, this is not always the case, and that's what we're going to explore here. So you have a map from the mapping telescope of M to the group completion, which is just coming by comparing these colimits, and I'm abusively using x also for the image of x in pi naught of the group completion here. Hopefully this doesn't create. But since M is a group, this map is an equivalence, so this was just the group completion. If you want, because if you take minus x plus gives you exactly an inverse to this x plus. So we have this map, and this map, you wish this map were an equivalence, but it's not in general. So let me give you an example where this is not. And this is an important example. So let M, so let let M be the symmetric monoidal groupoid.
Excuse me, a short question.
Yes.
In the example above, did you mean that x is then going to be 1 or for x equals 1?
I mean, you choose, you choose x is part of the data. I'm giving you a monoid and an element x. And here I'm telling you which element to choose.
Okay, so for any monoid and x equal 1, we
No,
get...
not for any monoid, for this monoid. The natural numbers under addition.
Oh, okay, so for... Oh, okay. Okay, thank you.
For this particular monoid, which is actually the same monoid that will show up in this example of free, say, R mod modules where R is some commutative ring. It doesn't even need to be commutative, but I don't care. I'm going to do a very special case. And so this is an E-infinity space, because we discussed that symmetric monoidal structures are the same thing as commutative monoid structures. I didn't prove it, I said it was a classical theorem. If you want, it's not actually that hard to construct explicitly the E-infinity structure in this case. But I don't want to in any way. And here I'm going to pick X is going to be, so M as a space is the disjoint union of B, G, L, and R. So this is just, you know, the groupoid. This is automorphisms of Rn. And its group completion is what's known as the free algebraic K-theory of R. In general, if you want the algebraic K-theory, you need to take the commutative monoid, sorry, the projective, finitely generated projective monoids. And oh, forgot. I always forget in this setting. If you don't put finitely generated, it turns out that you get 0 in the group completion. But I'm going to. And this space is very hard to study. But the point is that pi1 of the group completion is abelian, because whatever it is, it's an infinity group. And so you know that its pi1 has to be abelian, because the pi1 of any H space is abelian. We saw this last semester. Now, what is the telescope? Oh, sorry. In this case, pi0 of M is n, given by the dimension of your free R module. And I'm taking x1 as before. Now, what is the telescope of M? Well, it's the colimit of these maps, where the map x plus on each connected component is just BGLN of R to BGLN plus 1 of R. That comes from the map of matrices that sends a matrix A to the block matrix, like this. This is I'm adding a one-dimensional factor on the right-hand side. And so if I have an automorphisms A from V to V, the automorphism on V plus 1 is exactly this thing. Oh, I didn't say the symmetric model operation with operation direct sum. Sorry, someone should have asked what the monoid operation here was. It's just the direct sum. Okay, so what is this colimit? So this turns out to be just Z times BGLR, where GLR is the group of matrices, of infinite matrices that are the identity outside of some finite block. If you unwrap what it is, this is what it is. And in particular, pi1 of tel x m is GL of R, which is not abelian. And that is a problem. And that is actually why algebraic K-theory is both hard to study and interesting. This mismatch between what you naively would think it is and what it actually is. Okay. So, you know what? I don't think I'm going to be able to do the whole proofs, so I'm just going to tell you the important definitions and an idea on how these things work. So important definition is the following. So suppose f from x to y map of spaces, it is acyclic if for every y in y, the fiber xy, and remember I'm working homotopy everything, so I do mean the homotopy fiber here, has the homology of a point. So this is z for star 0 and 0 otherwise.
This is not the same as a homology ISO?
No. In fact, that's a first example. That's an exercise / example. Well, no, it's an example. Actually, no, let me put it a lemma. Here, even if I don't prove it, I want to record some consequences. So f is acyclic if and only if the square here, so here I have f, identity of y is a push-out square. And I mean a homotopy push-out square. And okay, the proof is not hard, but instead of the proof, let me recall a bunch of corollary. So if, so every acyclic map is a homology ISO. Because you just take this push-out square and look at the long exact sequencing homology of this homotopy push-out square. And you see that this forces them up to be homology ISO. And if y is simply connected, every homology ISO f from x to y is acyclic. And that's because since it's a homology ISO, the map from the push out to y, because then the map from the push out to y is a homology ISO between simply connected spaces. And the push out is simply connected by Van Kampen. You know, every time you can cover everything with two simply connected things in a connected intersection. So, but it's not, the vice versa is not true if y is not simply connected. And it is sort of true in the sense that it is true if you ask the map to be an homology for an ISO on homology for all local coefficient systems. But if you've never seen homology with local coefficients, that's all I want to say for now. I don't know if that answers your question.
Yes, that was what I was wondering.
Okay. And okay, why am I doing this? Because there is this important theorem called the group completion theorem. That says that if mx as above, then the map from the mapping telescope into M is acyclic. In particular, M group completion. In particular, we will consider a case where the mapping telescope is simply connected, in which case the map will be an equivalence, because a cyclic map between simply connected spaces are equivalences. And in fact, actually, let me prove as likely. So how much time do we have? Let me give you some ideas of how the story continues. Yeah. Is it clear so far? This will allow us to give an explicit description of the group completion in terms of the mapping telescope, actually. Okay, so let's close it. Okay, so I need to recall a couple of group theory definitions. So G, a group, is perfect if the abelianization is trivial. This you should have probably seen it before, and it's hypoabelian. Sorry, every group has a maximal perfect subgroup. A unique. That's because if you have two perfect subgroups, the subgroup generated by them is also perfect. Since perfect, it means that it's generated by commutator of its elements. So if you take the subgroup generated by two groups, you can just take all the commutators of elements in the first group and the commutators of elements in the second group, and they need to generate everything. So this is perfect. So you can just take all the perfect subgroups and take the subgroup generated by all of them, and they're also perfect. So G group is hypoabelian if the maximal perfect subgroup is trivial. This you probably haven't seen it, but it's sort of a weakening of the notion of an abelian group. Of course, for an abelian group, well, every abelian group is hypoabelian, but we need this slight generalization. And we say that a space Y is hypoabelian, X, let's say, is hypoabelian if for every X in X, the fundamental group is hypoabelian. It's just going to be a convenient shorthand when the space is not connected. I'm just going to say the space is hypoabelian to mean that all its fundamental groups are hypoabelian. Okay, and then there is this lemma that suppose f x to y a cyclic map with x hypoabelian. Sorry. Then f is an equivalence. And okay, why am I doing this? Okay, how do I prove this? It's enough to prove that every homotopy fiber is simply connected. Because then it's we know that it has the homology of a point, and then the Urevich theorem tells us if it's simply connected and has the homology of a point, then it is contractible. Urevich. And we know that if every homotopy fiber is contractible, the map is an equivalence. As we discussed last year. And okay, so let's pick y in y. Then you have an x in the homotopy fiber. Then you get can get an exact sequence of homotopy groups. But we know that this guy is perfect because its abelianization is the homology of the homotopy fiber, which is 0. And the quotient of a perfect group is perfect. So this map lands into the maximal perfect subgroup, and so it's the zero map. And henceforth, this is a quotient of pi naught, pi 2. But pi 2 is abelian. This is hypoabelian. And well, okay, it's an abelian perfect group. There aren't that many of those. Okay. Let's see, how much do I want to say about the next? Okay. Let me just put this theorem here. So for X, any space, there exists a unique X to X plus a cyclic map with X plus hypoabelian. It's called the Quillen plus construction. And I'll explain in a second how do you construct such a gadget. Moreover, every map XY with Y hypoabelian factors through X plus. I'm not sure if I'll do the complete proof of this theorem, but as a corollary, we have our acyclic map given by the group completion theorem. And note that the target here is hypoabelian. It's the pi 1 is abelian even. So these factors through this is an acyclic map, this is an acyclic map, and in fact, you can check with some care that acyclic maps do satisfy the 2 out of 3 property using the push-out criterion I told earlier. And so this is an acyclic map from a hypoabelian space. So it's an equivalence. That is, the group completion is the plus construction of the mapping telescope. And as you will see in a second, I'll give you the explicit construction of the plus construction is very explicit. You can just write it down. So let me give you the construction of the plus construction, and then I will see how much time do we have. I think I'll probably better spend it to answering your question than to giving the proofs of the missing statements that are in the notes. You can actually give a complete proof of the group completion theorem and everything using these ideas. Yeah, let me just give you a construction of the plus construction so that at least we have something concrete in our hand. And so let's construct such X plus. So let's first do the case. So we can do it on each connected component. So let's assume X connected, because acyclic maps only care about connected components anyway, and hyperbolian is likewise. So first, let's do the case H1X is 0, or if you want, the pi1 is perfect. So let's take alpha I, sorry, S1 to X, generators of pi1 of X. Then we can consider the following fiber sequence. That is, we are attaching a 2-cell on each alpha I. So for the co-fiber sequence, i.e. 2-cell for each alpha I. And then notice that pi1 of X prime is 0 by Van Kampen. But this map is not acyclic, so something is going wrong. So let's look at the long exact sequence in homology. So what do I have? I have H2 of this guy, which is 0, mapping to this right? Yes. H2 of X, mapping to H2 of X prime, mapping to H1, these guys, mapping to H1 of X. Now, the point is that by the choice of the alpha I, sorry, we said that X we said that X is H1 of X is 0. So, and this is just a free module over I's. So we have H star of H prime is just H star of X if star is different from 2, and H2 of X plus this free guy if star is 2. I didn't do the case of the other homology groups, but that's trivial since the homology of the wedge in that case is 0. So nothing interesting happens there. So we need to fix that. Now we have pi1 of X prime is 0. So H2 of X prime is the same thing as the pi2 of X prime by Hurewicz. And so we can find beta I from S2 to X prime, picking a basis for these things, for this summand, the summand that we want to kill. And now we just cone off all this bi, and we get a space that I'm going to call X plus. X plus is still 0, it's still simply connected. And now the long exact sequence in homology shows that the composition x goes to x prime goes to x plus is a homology iso. Henceforth is acyclic, since the target is simply connected. Okay, so this was the case where H1 was 0. Very easy, just attach a bunch of cells. And now so in the general case, we have P in pi1 of x maximal perfect subgroup. Then you know that there is x tilde into x covering space associated to P. So in particular, pi1 of x tilde is P, and so H1 of x tilde is 0. So we can consider the following, the construction as before of x tilde plus, and this maps to x, and you can take the push out and get x plus. And so this map was acyclic, and using the push out criterion, it's easy to say that acyclic maps are stable under push outs. Essentially because a push out of a push out is a push out. Let me just quickly draw the cube that you need. Sorry, W. I want to say if all the faces but one of this cube are push outs, so is the last one. And so this map is acyclic, and then by Van Kampen, pi I of x plus is pi I of x mod P is hypoabelian. Sorry. And okay, I don't have time, I think, to prove that it's the unique one and to give all the details and to prove this criterion for the push out, which is all in the notes. But I just wanted to show you that this is very, very explicit. This plus construction. Although this doesn't really help us computing the homotopy groups of the plus construction. Because, you know, every time you attach a bunch of cells, the homotopy groups can do crazy things. And in fact, they do crazy things. But still, it's not. Okay. And if this vague, quick thing puzzles you, the upshot of this is going to be this. And in fact, we are actually very close to be able to prove the group completion theorem, but I don't think I want to continue with this story. I think I'm going to put everything in the notes, but not say more, because I want to talk about vector bundles also. So, okay, so that's it. Are there questions?
Excuse me, could you please scroll back to the end? Not finished.
Yes, sorry. Sorry. Maybe, okay, it's going to be written in the notes, but I should also mention that for the plus construction, I'm following these notes by Marco Iwa, which is literally called, I think, on the plus construction or something like that. I'm going to put a link. It works in the context of arbitrary infinity topoi that I'm translating the proofs for spaces and putting them in the notes. It's convenient to work sometimes the plus construction for sheaves of spaces. That's why he's working in this added generality. But the proofs are fairly elementary, in fact. You don't need much. And yeah, I think that on Monday I'm going to start talking about vector bundles. Oh, and actually, yeah, let me put as a corollary, like this free K theory that I defined before is Z times the plus construction of BGL R plus. So it's construction on BGL infinity R. That's the definition that sometimes they give in elementary classes, and it seems like super confusing. Why would I ever consider this object? And that's because it's the group completion of the monoid of free R modules, which is a much more reasonable definition of algebraic K theory, in my opinion. And then, unfortunately, this is not a class on algebraic K theory, so there will be a lot more to say, but at least the definition, since we can give it.
Could you maybe simply again explain what the plus construction should accomplish?
A plus construction, so the point is you have this telescope here. Go back here. You have this telescope here, and you really would like it to be the group completion, but there might be a pi1 obstruction, because the group completion wants an abelian pi1, and this guy in general might not have it. So the plus construction just fixes this. That's the point. Plus construction makes it so, okay, the pi1 is not abelian, it's hypoabelian, but okay, it turns out that that's enough for running all the arguments we want. And in this case, it will be abelian. And in fact, actually, the way you prove this theorem is to prove that this map is an equivalence if pi1 of M is hypoabelian, and use that the plus construction commutes with what do you say it, with products to get a commutative diagrams like this. And this is going to be an equivalence because M plus is the pi1 of M plus is hypoabelian, and this one is an equivalence because it's still an acyclic map with pi1 hypoabelian, and this is an acyclic map. And so this is acyclic. That's one possible proof of that group completion theorem. It's not the original proof, but I like it. It's due to Thomas Nikolaus, I believe. Yeah. I'm going to put references to all of these in the notes. So hopefully this sort of justifies why the plus construction needs to be introduced. And I also have to say that, okay, let me actually stop the recording unless there are other questions.